Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue this new mini-series on measurements. In this clip, we share several horror stories of just how bad nip control can be, even on brand new, state-of-the-art winders built by name brand builders. However, the lessons here are not limited to layon rollers or even fluid control. They are much more universal. That is, check your sensors, check your controls, and check your work. I know your time is precious, so let's get started. As a consultant, one of my earliest experiences with a truly naughty nip was for a winder I worked on about 30 years ago. At that time, it was a brand new research lab winder built by a brand name builder. It was in an era when PLCs could just begin to do some math beyond the simple four functions. In any case, we started up the winder, and I asked the control engineer to set the nip to plus 5 PLI, a very normal value for that web product and that web machine. The nip opened up. That was clearly not a plus 5 PLI nip. That wasn't even a 0 nip. Digging a little bit deeper, I looked at the math inside the PLC for computing the nip in engineering units given nip cylinder pressure in PSI. It was done with 7 digits of precision. However, as the computer saying goes, garbage in, garbage out. Next time and every time, the engineer should check his or her work, as I show how to do in my Web201.71i through F series on nip control calibration on this all web handling channel of YouTube. Even better yet, as I was taught as a young design engineer, we should first check our work via calibration or other independent method, and then someone else should recheck our work, even if it is only simple high school trigonometry that was required. Fortunately, in this case, the fix was simple. Redo the math on paper and then in the PLC program and then recheck it again. Not all cases can be simply fixed, as we will see in the next 2 slides. Another collective experience of naughty nips is with another level rail rear winder. This one is similar to 1,000 others found at the end of nearly every paper machine ever built. In this specific case I worked on 3 years ago, the reel was making tight wound roll defects and was winding even tighter than the 2-drum winder that follows. That can be easily checked with roll hardness measurements as I teach in the advanced section of my Web 101 course. In any case, a normal nip load for this product in this machine would be around 10 PLI. I measured the nip friction. This can often be done in just a few minutes, as I show in the nip calibration series below. The nip measured to be 25 PLI of friction. What that means is, if you set the cylinder pressure to 0, you get 25 PLI of nip, whether you want it or not. What that means is that the noise to signal ratio, not the signal to noise ratio, is 2.5 to 1. What that means, as shown in this load cell readout, is that the actual nip, not the one the computer sees, is not only way too high with 0 cylinder pressure, it is extremely variable. There are known and field-proven solutions to this design problem for this specific type of winder, as I teach in my advanced winding class. They work quite well, as shown in this before and after graph. However, and this is a big however, you will have to replace at least half of the winder to do it, and it would be a custom design and quite expensive upgrade. This next case of a truly nasty nip was on a 2-drum tissue winder. Since tissue is much more delicate web, we would desire even a lower value for nip loading. 5 pli would be a lot for even the tissue you find in airport bathrooms, and the stuff you would buy for your own home would be wound with 1/10 of that nip. In any case, I measured the nip in just a few minutes. It clocked in at 35 pli, a noise to signal ratio of 7:1. What that means is that the pressure knob is a do-nothing knob. It makes no difference where you set it. There is absolutely no hope for that machine except total replacement. Before we leave the topic of upgrades, I will share another experience with this type of winder that was upgraded to what is called anti-friction slideways because they had linear bearings of the old-fashioned gib type. The results were that not only did this so-called upgrade not reduce friction, it more than doubled friction, using what were considered precision bearings. Not only that, the precision bearings wore out in years rather than the decades of the old-fashioned greased gibs. This is not uncommon that upgrade makes problems worse. While the idea may have been fine, the details were missed in the rush to get the job out the door, and of course, the engineer did not check his work in the field. One more note, and this is a big important one for maintenance. This is very seldom can be fixed by greasing or oiling. If maintenance were an issue, and it sometimes is but rare, it is usually caused by binding of some moving parts that are misaligned. Much more often, however, the root cause is a design problem, and the solution would be a redesign. This example of a naughty nip shows the potential for misbehavior in even the most advanced engineered system. This was a brand new $10 million winder made by a brand name builder. It was instrumented far better than at least 99.9% of all winders in the world. Just for one example, they were taking data for more than 20 sensors, such as nip, load cells, and motor, at rates of 1,000 samples per second, and sending every single bit and byte to an offline analysis service for continuous real-time monitoring for abnormalities. In any case, I and other experts were brought in to find out why they were having such a high level of nip-induced defects on this brand new winder. It had costed the mill about $1 million in waste and customer complaints in the first year after startup. After a bit of checking, the senior engineer from the builder, a good friend and colleague, found a divide by 2 error in the PLC program. In other words, the actual nip was twice as high as the program thought. Fortunately, this had a simple solution. Remove the divide by 2 in a single line of PLC code. The coding and calibration problem, costing $1 million a year, went away overnight. Now, I don't want to leave you with the impression that nip controls are always loaded mechanical friction and calibration errors, even though it's not all that uncommon. I was on another two-drum winder with precisely the same nip-induced defect. This one had an extremely complicated geometry for nip control, and that complication made me even more suspicious. So of course, I made a quick check of calibration and friction, both at the same time and taking only a few minutes. With the winder mostly locked out, I asked the control engineer to trick the PLC into setting the nip to 0, which is normally not allowed during run for safety reasons. I went over to the 10-ton layon roll assembly and found that I could move it by hand. Very close to 0 nip and a friction of only about 50 pounds, or in relative terms, an uncertainty in real nip load of only a few percent of set point. Darn good German engineering in this one quite specific case. So the bottom line is this: you never know for sure until you check. Even with the accumulated field experiences in about 1,000 plants, I might still have to do the checks to be sure about the more important web machine settings. I hope you enjoyed these stories of rather ordinary experiences from the field. I hope that this inspires you to be more thoughtful when dealing with instrumentation and controls. There are 3 starting points for more detailed discussion of problem solving and instrumentation. The first is my nip control calibration series, Web201.17a through F, on this all web handling channel of YouTube. The second is the must-have 750-page Web Handling Handbook, written by myself, Tim Walker, and Dilwyn Jones. This is where you would look for the targeted and objective measurements for most web and roll defects that are science-based, and that can help you from going on unnecessary and fruitless fishing expeditions. Last but not least is my award-winning and trademark Web 101 class that has been taken by about 5,000 people, just like you. Here you will learn about web handling, winding, common converting operations like slitting, as well as a good sprinkling of problem-solving techniques, such as how to measure and calibrate nips, as just one example. Thank you so very much for joining me in this Measurement Miasma mini-series. Please join me next week, where we will again continue our discussion of web handling and related topics. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.